let's do some practice. Okay, so let's look at the first one where we are talking of R is equal to the set of integers under addition and multiplication, right? So here what I find helpful is to have something like this, right? So the advantage is I can keep referring to it and keep taking care of it one by one. Now, for a simple example like this, where we are talking of integers, we can directly take care of it because we know integers. They are closed under addition, associative. But still, if you have to write it, you can just write it in short. That is closed under addition. So A plus B belongs to R for all A comma B belonging to R. That is closure. So that's taken care of. Okay. Associative under addition. So A plus B plus C is equal to A plus B plus C. We know that that is also true for all A, B and C belonging to R. Okay, third one is additive identity exists. So 0 is the additive identity. So A plus 0 is equal to 0 plus A is equal to A, right? For all A belonging to R. So additive identity exists. Now, additive inverse minus A, there exists an element minus A such that A plus minus A is equal to 0, right? So you have an element A, you have a negative A, which is the inverse. So if you add the element and its inverse, we get the additive identity. So additive inverse exists. Addition is commutative. Again, we know A plus B is equal to B plus A for all A comma B belonging to R. Okay. So addition is commutative. Closed under multiplication. So A times B belongs to R for all A comma B belonging to R. We know that, right? So it is closed under multiplication. Associative. So A times B times C is equal to A times B times C for all A comma B comma C belonging to R. Because remember, we are talking of integers. Okay. So that means it is associative under multiplication. Now, multiplicative identity. So, 1 is the multiplicative identity, right? So, A times 1 is equal to 1 times A is equal to A for all A belonging to R. Okay, so multiplicative identity exists. Multiplication distributes over addition. So, we know A times B plus C is equal to A times B plus A times C, and B plus C times A is equal to B times A plus C times A for all A comma B comma C belonging to R. Again, because the integers is having this property. Now, as you know, different authors and different textbooks, either they insist on the multiplicative identity or they don't insist, right? So there are two schools of thought. So you need to be clear about which particular textbook or school of thought you are following. According to that, either multiplicative identity needs to be identified or needs to be there for you to call it a ring or not. Okay, so in places where they insist on a multiplicative identity. Remember, in that case, it's not called a ring, it is called RNG. That means a ring without the I. That is identity. So depending on that, you have to say whether it is a ring or RNG. Okay. So that is, so that way, if, what we have achieved is, now we are in a position to say R is a ring because it contains the identity, multiplicative identity, and this is multiplicative. Okay. Again, you need to be clear about which particular textbook you are following. Okay, let's look at the second one. Again, Gaussian integers. Okay, these are numbers which are of the form a plus ib, right? Where a and b belong to the set of integers. And in short, we can call it as j of I. Okay, again, like before, let me copy paste this and we can use it as a reference point. So, we know complex numbers, remember, Gaussian integers are nothing but a subset of complex numbers. So complex numbers are closed under addition, right? And j of I is a subset of complex numbers. It's a proper subset. So I should not put that. Proper subset of complex numbers. Okay, second one. So this is done. Associative under addition. So again, complex numbers are associative under addition. So therefore, J of I is also associative. Additive identity exists. A plus IB belongs to J of I. Additive identity is 0 plus I 0, which also belongs to J of I because it is of the form A plus IB, right? No. What about inverse? Additive inverse. And now it will get confirmed whether this is actually the additive identity. So let's see. So here basically if you want to prove this, what you can do is you can say A plus IB plus 0 plus I0. If you add it, you should get back the A plus IB. So A plus 0 is A, IB plus I0 is IB. So it works out. Now the additive inverse is going to be minus A plus minus IB. Again, let's see. If we take an element A plus IB and we take its, if we add the additive inverse minus A minus IB, what do we get? A minus A plus I times B minus B, which is equal to 0 plus I 0, which is equal to 0, which is the additive identity. So we have additive inverses. So we have got additive identity exists, additive inverse exists. Now is addition commutative under addition? So again, A1 plus IB1 plus A2 plus IB2 is equal to A2 plus IB2 plus A1 plus IB1. They should be equal. So here this will become what? A1 plus A2 plus I times B1 plus B2. And here A2 plus A1. But remember A1, A2, these are all integers. Right? So integer addition is commutative. So we can write it as A1 plus A2. Similarly, B1 and B2 are integers. So we can write it as B1 plus B2. So Gaussian integers are commutative under addition. So addition is commutative. Now let's go to multiplication. Closed under multiplication, since complex numbers are closed under multiplication, right? Similarly, associative under multiplication, since complex numbers are associative under multiplication. Again, just keep referring to this, otherwise you might miss out. So it is closed under multiplication, associative under multiplication, multiplicative identity exists, right? So what would be the multiplicative identity? So multiplicative identity of a plus ib belonging to j of I would be 1 plus 0 I, right? Anything multiplied by 1 is the number itself. So we just put the 0 in the imaginary part. And this also belongs to j of I. So just to prove it, what we can do is, if we multiply a number a plus ib with its multiplicative identity, we should get back the original number. So a times 1 is a plus 0i plus ib plus I square 0. So this becomes a plus ib. So we get back the original number. So multiplicative identity exists. Multiplication distributes over addition. Okay? So multiplication distributes over addition. Okay. Now if you are not very clear about whether complex numbers distribute multiplication over addition, you can actually do it the hard way. So which means you take a Gaussian number a plus ib1 and another one plus a3 plus ib3. So here a1 b1 a2 b2 belong to integers, right? Okay, now let's simplify this. This is the LHS part of the distribution. Next we will take up the right hand side. So this would be a1 no a1 plus ib1. First we do the addition. So this becomes a2 plus a3 plus I b2 plus b, and now we multiply it. So what do we get? A1 times a2 plus a3 plus I a1 times b2 plus b3 plus I times b1 times a2 plus a3, and finally plus I square b1 times b2 plus b3. Okay, and here I square will convert this plus to minus. So finally we will end up with a1 times a2 plus a3 plus I we take common, or let's leave it as it is, I a1 b2 plus b3, or let's take it common, plus a no b1 a2 plus a3, and finally minus b1 times b2 plus b3. So this is our left hand side. Now let's look at the RHS. RHS would be, we actually take care of the multiplication, we distribute. So a1 plus ib1 times a2 plus ib2 plus a1 plus ib1 times A3 plus IB3. When we simplify this, we should arrive at this. So A1, A2 plus IA1, B2 plus IA2, B1 minus B1, B2. I square will become minus, right? Now, plus, now we look at this. A1, A3 plus I A1, B3 plus I A3, B1 minus B1, B3. Now this would be equal to A1, A2 minus B1, B2 plus A1, A3 minus B1, B3. This and this. Then plus I times A1, B2 plus A2, B1 plus A1, B3 plus A3, B1. Now, here A1 times A2 plus A3, right? Then we have minus B2 times, no, B1. So this would be B1 times B2 plus B3 plus I times A1 times B2 plus B3 plus B1 times A2 plus A3. Now, if you do the comparison, A1 times A2 plus A3, A1 times A2 plus A3, minus B1, B2 plus B3, minus B1 times B2 plus B3, I times A1 times B2 plus B3, and B1 times A2 plus A3. So, therefore, distribution of multiplication over addition is satisfied. So, we can take this as well. So, finally, we can say that Gaussian integers form a ring under addition and multiplication. I think that's enough for now. Bye.